Okay, so today we're going to build on part 1 of inventory management. We're going to cover 3 key ideas. Inventory management in a supply chain. We just looked at 1 point last time. Then we're going to talk about risk pooling, and then we're going to talk about service level optimization. So just 3 main ideas. So why are we even having this lecture? What is the problem in supply chains? Let's look at a simple supply chain: retailer, distributor, manufacturer. Okay. If this is the demand the retailer sees, average demand level of 1200 per week, standard deviation of 300. Okay. Now this retailer is working on make to stock, so they have some stock they sell from finished goods inventory. Okay. It's not like make to order where you take the order then you produce something. It's selling from stock. So they have inventory to sell the demand from. When their inventory runs low, like you saw the week before last week, when they hit the reorder point, they place an order with their supplier, which is the distributor. Okay? Whenever your demand filters through an inventory buffer where you have a reorder point type of system, the standard deviation of the demand is going to increase. This is without the bullwhip effect. Why? Because here customers come and place small frequent orders. The small frequent orders get converted into large infrequent orders here because you have an inventory buffer in the middle. Okay? Think about it this way. Let's say your consumption of toothpaste might be extremely steady, right? You might consume, I don't know, 1 ml of toothpaste or 5 mLs of toothpaste in a day, because you brush the same number of times in a day usually, and you use about the same amount of toothpaste. So your demand or consumption of toothpaste might be exactly flat. Okay, but you have some inventory of toothpaste at home. You have like a, a toothpaste in some container at home. When you run low, you go and you buy toothpaste. You don't buy 1 ml or 5 mLs. You buy like a whole amount of toothpaste from the retailer. So the retailer does not see that steady demand day by day. They see a bunch of toothpaste sold to you, and then you don't go buy toothpaste again for 2 weeks or something. Then you show up after 2 weeks, and then there's a spike on demand from you, right? So whenever your demand goes through an inventory buffer, it kind of becomes spiky and infrequent because you only go when your inventory gets low. So this guy sees more variability in demand. This guy will, let's say this distributor is supplying from their inventory to this person. They're not producing anything, okay? The finished goods inventory. When their finished good inventory runs low, they're going to place an order with their supplier. The order that comes up here will see even more standard deviation, because it'll be even more spiky and intermittent, okay? All of this is happening without factoring in the bullwhip effect. The bullwhip effect will make it worse. But even if there was no bullwhip effect, you'll see increase in variation because the inventory buffers are going to buffer the demand for a time period and then release demand in one big spike. Okay? So what happens is, if all of these people manage inventory themselves using QR system or PT system, whatever inventory management system they have, because this variability is increasing, the inventories will increase along the supply chain. And if each person does very excellent inventory management using their operations management formulas that we reviewed the week before, you'll have too much inventory in the supply chain. Okay? And the reason being that each one just looks at the demand they see, right? And they don't consider the whole supply chain in their calculation. Also, this guy may not see the end demand, and that guy may not see the end user demand. So they only see the demand to themselves. Now, if we could share this actual demand data across the supply chain, and if these 3 parties work together, they could reduce their inventories by a large amount without affecting any customer service. So without affecting stockouts, anything else, they could reduce their safety stocks and inventory levels. To do that optimally gets quite involved, and you have to use computer software to kind of optimize the inventories. But we have a very simple way to get to most of the benefit. Okay, so what we're going to talk about today is a good solution to managing inventories in a chain like that. It is not optimal, but it is close to optimal, and it's very easy to calculate using the formulas we've already studied the week before. Okay. To do that, we need to define two things. We need to define this idea what's called an echelon lead time. Echelon just means like a stage, and we want to define echelon inventory position. Okay. When this retailer is setting their inventory levels, they look at their lead time, which is 1 week. Right? This 1 week lead time goes into their formulas for safety stock, reorder point, all those formulas. Okay? In this echelon inventory management system, sometimes it's called multi-echelon inventory management, their lead time is not any different. Their lead time is again going to be just 1 week. Okay? When we get to the distributor, however, in the old system, distributor's lead time was this lead time between distributor and manufacturer, which was 1 week. Okay? What we're going to assume is, in our mind, we're going to move the distributor all the way here. Not physically, just virtually. So the distributor's lead time, echelon lead time, is going to be all of the downstream lead time plus the original lead time that was 1 week from the manufacturer. So if you look here, the distributor's lead time is from here all the way to their supplier, which is 2 weeks. Okay? For the manufacturer, we take all of the downstream lead time and then add the lead time the manufacturer has to get raw materials or whatever. Okay? So echelon lead time, as you go from retailer upstream, just keeps growing and growing and growing. Okay? Okay. If in the old system, the retailer ordered inventory from the distributor by comparing two things. One was their current inventory level plus the inventory which was in the pipeline on the way, already shipped out to them, and adding their inventory level to the pipeline inventory, they got their inventory position. If the inventory position fell below the reorder point, they placed a new order, right? That's how the reorder point system works. They will work the same way, but the distributor now will consider all the downstream inventory as its own inventory. So it will add this inventory plus this, plus this, plus the pipeline inventory, and compare the sum of all that to its reorder point and then place reorders. Okay? That's called the echelon inventory position. So let me show you here in this graphic. So you can see the retailer is just doing this plus this, which is what they were doing previously. The boxes are pipeline inventory, which is on a truck on the way. Okay? The distributor does all the downstream stuff plus the pipeline inventory coming to it, so that's all of this. And the manufacturer does all of the downstream stuff plus its own inventory plus its pipeline inventory. Okay? So the idea is really simple for both of these variables. For lead time, we add all the downstream lead time plus our lead time. That's echelon lead time. For inventory position, we add all the downstream inventory plus our inventory. That's the echelon inventory position. Okay? And all we do in the existing inventory management system formulas is to replace the lead times by echelon lead times and then calculate our reorder points and then manage inventory using echelon inventory position instead of regular inventory position. So it's just the existing system. We just change two variables with these new definitions, and the results are pretty remarkable. So I'm going to show you the results, and we're going to do an example in detail to do all of this calculation. So let me show you the results first. Okay. So I ran a simulation, 3-stage supply chain, okay, and the calculations showed that I should get a 60% reduction in safety stock levels without affecting customer service. This is pretty huge. If you reduce your safety stock by 60%, that means your inventory holding cost has basically halved, right? But I have the same service levels, same inventory availability as before. No effect on customer service. Just to check the calculations, I ran a simulation. Obviously my simulation, I did it in Excel, so I only did it like a few hundred times, and I got a pretty close reduction as the calculation, so the calculations were reasonably accurate according to my simulation as well. Now, to do this though, imagine what's required. Distributor needs to know all the downstream inventory position all the time. So they need to have an IT system link with the retailer where they can check the retailer's inventory to do this system, right? Manufacturer needs to know all the downstream inventory. Plus, all of these guys now are only working on the actual end consumer demand. This guy does not use this standard deviation calculating safety stock. Everybody's using this demand now because they can all see the end user demand. So you have to share demand data all across the supply chain. You have to share inventory data all across the supply chain for this to be possible, for you to get these savings, okay? So sometimes that's not easy to do. Any ideas why that could be hard, sharing demand inventory data along the supply chain? Right, so there's many reasons. Some of them we discussed in our first couple of weeks, right? You could have some retailers which are like mom and pop stores. They don't have an advanced IT system. They can't share their demand. You could have issues of trust. You could have issues of confidentiality, right? Some retailers might do it with their large suppliers, like Walmart would do it with P&G. But if Walmart is just testing an SKU with a new company they don't know much about, they might not do it to start off with, right? So it kind of depends. You may not be able to do it for all of your products. You might do it for some of them. If you do it, the savings are pretty remarkable. So let's do an example. Okay, we have a supply chain very similar to what I showed you on the board. So we have a three-stage supply chain: retailer, distributor, manufacturer. The retailer faces an average demand of 45 per week on average. Standard deviation is 32. We don't care about the demand at the distributor and the manufacturer, right? Because we're just going to use the end user demand at every single stage in this new system. Okay. We want to keep a service level of 97%. That means a Z-score of 1.88. How do I go from here to here? I look this up in the Z table from a stats book, or I type equals norm.s.inv in Excel. When you give it 0.97 to norm.s.inv, it gives you 1.88 as Z. Okay. The SCM inventory workhorse Excel file has the formula built in. Just put in this number there. In service level, it'll give you the Z value there. Okay. Okay, lead times are given in the next slide, so we need to figure out how does the echelon system work out. Okay. Okay. So the retailer, when they order replenishment from the distributor, the lead time is 1 week. For the distributor to get it from the wholesaler, okay, so actually it's a 4-stage supply chain, is 1.5 weeks. Wholesaler to manufacturer is 2 weeks. Manufacturer to their suppliers is 2 weeks. The lead times in the supply chain. Okay. And then we have the holding cost. You can see inventory is expensive to hold here. Inventory is cheap to hold here. Any reason why? Right, this is raw materials, cheaper stuff. This is finished goods, expensive stuff. Plus retail space is more expensive. The manufacturer might be, in a cheaper locality. And so you can see as you get close to the end customer, usually retail space becomes more expensive. That's part of it. Also, at each stage, the holding cost depends on the cost of to bring the item at that stage. So the transportation costs get added to the cost, and the holding cost is a percentage of the cost. So that also kind of goes up. Okay. We don't really need the ordering cost. That's if you want to calculate the queue, the batch size. Okay. So first thing, we're going to convert the lead time to echelon lead time. For the last stage in the supply chain, it's the same one. Nothing changes for the retailer, right? So if you get a question on the exam and you have no idea what any of this stuff is, you could still do the retailer because nothing changes for the retailer. Just do regular inventory management for the retailer, right? Same lead time, same everything. For the distributor, the echelon lead time will be the lead time for the distributor plus all the downstream lead time, which is the retailer's lead time. So the 1 plus the 1.5. If you go back, is this, right? Downstream lead time plus your own lead time. These two. Okay. If you look here, what's going to be the echelon lead time for the wholesaler? Sorry? It'll be this plus this plus this. Yeah, 4.5. So all the downstream one is just 2.5 plus the 2. For this guy, it'll be the 4.5 here plus 2, 6.5. Okay, excellent. Now, once we have the echelon lead time, We plug the echelon lead time into our safety stock formula. The Z is 1.88. This is the 32, the end user demand. So we'll use the same end user demand in all the stages. We'll not look at the inflation in demand across the stages because our goal is just to meet the end user demand at the end of the day. Okay, so we'll use the standard deviation of demand, which is 32 from the end user, which is the retailer faces. We use the echelon lead time, use the Z, we get echelon safety stock at each of these levels. Okay? And then for reorder point, it's also very simple. You take the demand during lead time, demand times the echelon lead time, plus the safety stock. These formulas are exactly the same for a regular QR system. The only thing different is the L has become LE. Okay? Otherwise, if you go back to the part 1 slides, you see these formulas there. They're exactly the same. The only thing I'm doing is replacing the lead time with the echelon lead time. The second change I'm making is that the demand parameters, average demand and standard deviation of demand, I'm using the end user retailer demand at all the levels. I'm not saying, okay, the manufacturer sees the demand from the wholesaler, so this should be the demand statistics here. I'm using the demand the retailer sees for all 4 stages. So only these 2 changes. Okay? Now, the echelon safety stock means the safety stock for the retailer is going to carry 60 units. But this guy is not going to carry 95 units of safety stock because echelon safety stock says safety stock at this point and downstream should be 95. So safety stock from here downstream should be 95. Well, here I have 60, so I need an additional 35. So the actual physical stock will be 60 here, 35 here. Okay? Because echelon safety stock was just going to mean in all of the supply chain till this point, that's how much safety stock we need. Echelon safety stock of 128 means that in all of the supply chain till this point, I need to have 128 units of safety stock. Okay? So how much will I have just at the wholesaler? Right, you do 128 minus the 95. Right? Because till the next stage you want to have 95, till this stage you want to have 128, so the additional is 33. Okay? The manufacturer, the echelon safety stock tells you in the entire supply chain you need to have 153 safety stock. Right? Till the wholesaler you already have 128 done. So what's the additional? 153 minus 128, that's the one this guy's going to carry. Okay? So we have how much safety stock to keep, and the reorder point we can manage our inventory. Whenever the echelon inventory position goes below the reorder point, we place an order with our supplier. Okay? And that's how we manage inventory in the supply chain. These, if you were to calculate, using the regular formulas, well, first of all, you'll need demand at each stage. So you would also need, for each stage, what is the demand they see, the average demand, the standard deviation of demand. And if you would do it that way, you would get inventory levels which are much higher than these levels. Okay? Although they would give you the same service level eventually as these would give you. Okay? Now, I do want to point out one thing when you use these formulas. We were assuming in our supply chain everybody's selling from stock. At some point in the supply chain, you're going to switch from make to stock to make to order. So let's assume in this case, the manufacturer does not keep finished goods inventory. They get a forecast from the wholesaler, and when the wholesaler places an order, then they manufacture and ship that order out. So they have a longer lead time, but they manufacture after getting the order. If you are doing make to order, then you don't need this echelon inventory management at all. Then you just look at the orders you get, you have some reserved raw material, you produce to order. Okay? This echelon inventory management is only when you're doing make to stock. So if you have, let's say, a 6-stage supply chain, the first 3 stages are make to stock, you do the echelon inventory management in the first 3 stages, then when you convert to make to order, then you don't do echelon lead time for those stages. Okay? So if you go back to week 1, we talked about a push-pull boundary in a supply chain. Push is make to stock, you're making before getting the customer order. So you have a push part of the supply chain, and eventually you'll get pull part where you'll be making to order. So you don't do this in the pull part of the supply chain where you're doing make to order. Okay? Then you just get the orders and the forecast of demand. So a lot of manufacturers, they will do intermediate level processing on a forecast and do the final steps when they get the final customer order. Right? So they don't need to do the echelon inventory management. They're doing make to order. Okay? Okay. So, any questions about these formulas? All the calculation is done in this Excel sheet which you have. So if you go to Blackboard, I've already uploaded this Excel sheet which has this exact calculation done. The formulas are built in, so you can review all the computation here. Okay, let's go to the next part, which is risk pooling. So let me show you what the main idea of risk pooling is. Okay. Risk pooling is the idea that if you have demand across different regions or different product categories, the sum of the demand is going to have less variability than the sum of the variabilities in the individual components. So let's look at this example. I have 3 regions where I sell my product. Each region has some average demand, some standard deviation of demand. So region 1, on average, I sell D1 per month. Standard deviation of demand is sigma 1. Region 2, I sell D2 units per month, sigma 2 the standard deviation. Region 3. One way to satisfy this demand is to have a warehouse in each region. So I have 3 warehouses, right? And each warehouse supplies the retailer and satisfies the demand. If you have 3 warehouses, each warehouse is going to have inventory based on this demand. So you'll have warehouse 1 having inventory to meet demand here, whereas 2 having inventory to meet this demand, whereas 3 having inventory to meet this demand. An alternative to having 3 warehouses is to have what's called centralization, just have 1 warehouse supplying to all 3 regions. Okay? When I have 1 warehouse supplying to 3 regions, the demand this warehouse will see will just be the sum of the individual demands, D1 plus D2 plus D3, right? Region 1 sells 10 units, region 2 sells 20, region 3 sells 10, 10 plus 20 plus 10, you'll satisfy 40 units on average. So the average demand just adds up. However, the standard deviation here is not going to be sigma 1 plus sigma 2 plus sigma 3. Okay? You can't add standard deviations like that. Why? You have to go to probability distributions and do some calculus to see exactly why. Or you can't add standard deviations, but you can add variances. So sigma 1 squared is the variance. You add that to the second variance. You add that to the third variance. You get the total variance, take the square root to get the standard deviation here. Okay? The nice thing about this formula is that sigma t is going to be less than the sum of sigma 1 plus sigma 2 plus sigma 3. Okay? So let me just show you in Excel. So this is again is in the risk pooling slide. Here I have 3 regions demands. Okay? The average of region 1 is 107, region 2 is 97, 99. Standard deviations are given here. If I add these 3 standard deviations, you can see the sum is 56. Okay? But if I just sum these columns up and I compute the standard deviation of this summed column, the standard deviation of the summed column is only 30. Okay? It's not 57. So there's a 47% reduction in the demand variability by adding demand across 3 regions. Okay? And if we go back to our safety stock formula, if this sigma d falls by 40%, the safety stock falls by what? 40%. It's directly proportional, right? So whenever your standard deviation is going to fall, safety stock is going to fall by the same amount, right? So when you aggregate the demand across 3 regions into 1 warehouse, so 1 warehouse supplies all of the demand, the safety stock in this warehouse will be 40-something% less than if you had 3 warehouses supplying these 3 regions. Why? Because the standard deviation of demand is that much less of the total. Okay? That's called the risk pooling effect, because what you're doing is you're pooling the risk or the variability from 3 sources into 1. And when you pool variability together, some of the variations cancel out. One thing goes low, one goes high, they cancel out. So that canceling out is saving you on variability, which is saving you on safety stock. Okay? Now, this formula only works if these 3 regions are completely independent demand. They don't move together. Okay? Which is nice because it makes the math very simple. And for this course, that's all you need to know. Okay? But in real life, it often happens that different regions have correlated demand. So if, people have worked, you guys have all kind of worked in different industries, if something becomes popular on the East Coast, there's a bigger than zero chance it's going to become popular in Midwest, and a bigger than zero chance it's going to become popular in the West Coast too. Right? It's not that West Coast moves totally independently from the East Coast, from the Midwest and things like that. Right? Popular things become popular all over, unpopular things become unpopular all over. So some correlation in demand across different regions. If you do have correlations, the advantages from risk pooling decrease. So your formula becomes a lot more complicated. You have to put in the correlations between different demands here. This is not going to be tested in this course, so you can just ignore this one slide here, okay? But the reason it's there is because when you do this in real life, I don't want you to blame me and say your formulas were all wrong. You have the formula that you're probably going to use in real life there, but once you're paid for a job, you have more motivation to look into stuff and do it right, so you can use this if you need to, okay? Basically, so let me show you the example here as well. So you have the same example here, except that the first three columns are correlated. These are the correlations. So region A and region B have a correlation of 0.46. Region A and region C have a correlation of 0.3. Region B and C have a correlation of 0.19. When you do the correlation, you see the safety stock reduction is only 25%, whereas here it was 47%. So the benefit from centralization reduced, but still there is a benefit. Okay? So when you have, the only thing you need to know for this course is if your demands are correlated, it's going to reduce the benefit of risk pooling or centralization. It's still going to be some benefit. Okay? The only time you get zero benefit if the correlation is exactly 1. If they exactly move together, which almost never happens. Correlation is almost never 1. Okay? So there's always going to be some benefit of correlation. The best case benefit is given by this simple formula here. You can calculate the total standard deviation and then use that and see how much is the reduction in this compared to this plus this plus this. Because if you have 3 warehouses, you're going to doing inventory 1 based on sigma 1, inventory 2 based on sigma 2, inventory 3 based on sigma 3. Right? And then if you have just one warehouse, you'll do inventory total based on sigma total. Okay? So you can actually calculate it. You have the demands, you have the standard deviations, you can calculate the safety stock for the warehouse 1, you can calculate safety stock for warehouse 2, you can calculate safety stock for warehouse 3, and if you have a one warehouse situation, you can calculate safety stock for the one warehouse situation using these parameters, and you can see the reduction. Okay, you can do all these computations. Okay. Okay. So let's look at an approximation to get there quicker first before we go into a more detailed example. Now, because you might be thinking, okay, let's, instead of going from 3 warehouses to 1 warehouse, what if I went down from 3 to 2? Or if you have 5 warehouses, instead of going from 5 to 1, what if I want to go from 5 to 4 or 5 to 3? So I'm going to do some centralization, but not all the way to 1. Okay? So this square root rule is a quick and easy way to check how much your inventory will reduce if you go from any number of warehouses to any other number of warehouses in your system. Okay? So let's look at this formula. I1 is the total system inventory when you have N1 locations. Okay? I1 for N1. So let's say that's your starting point. You have 5 warehouses. I1 is total inventory in your 5 warehouses. N1 is equals 5. And the question is, what happens if you go down to 3 warehouses? N2 would become 3. And then I2 we don't want to find out. So I2, which is total inventory across 3 warehouses, is going to equal I1, the total inventory across 5 warehouses, multiplied by 3 over 5 square root. Okay? Now this formula gives you an approximate answer. It's not going to be exact because there's several assumptions. First of all, it assumes that demand in the regions being served by those warehouses is independent, which is almost never the case. There is some correlation which is going to reduce your benefit a little bit in real life. Okay? The other assumption is that these 5 regions are comparable. You're not comparing New York City to a small town in upstate New York, because the New York City warehouse is going to serve millions of dollars of demand, and this tiny warehouse is going to serve maybe thousands of dollars of demand. So you're not merging like a whale with a tiny fish, tuna or something, okay? You're having equal, approximately equal regions that you're comparing about whether you want to merge the warehousing for them or not, okay? So if those 2 assumptions are true, it will give you a reasonably accurate estimate. So let's do a quick example. Yes, suppose if you have $1 million, now this formula can work with dollars or units. You can, your I1, I2 could be just number of units of some SKU, but if your warehouse has multiple SKUs, just convert everything to a dollar figure. What's the dollar value of inventory? Okay, it could work in dollars, could work in units, doesn't matter. It's just a ratio. So let's say we have $1 million worth of inventory in 3 warehouses each, so 1 million each. Okay, so what would be my system inventory, the total? If I have 1 million each and I have 3 warehouses, 3 million, right? Okay, so I have 3 warehouses right now. I want to see what happens if I go down to 2 warehouses and what happens if I go down to 1 warehouse. I want to check both options. So if I want to go down to 2 warehouses, okay, my new inventory will be I2 equals 3 million is my current system inventory, 1 million each in 3 warehouses, multiplied by 2 over 3 square root. This is N2, this is N1. So the total inventory in 2 warehouses will be 2.45 million. And about half of that in each. So it will be about 1.2 something million in each. Total will be 2.45. So how much did that save? My inventory reduction went from 3 to 2.45 million, about 0.55, about 0.55, 0.6 million was my inventory reduction from going from 3 to 2 warehouses. Okay. Now if I go down from 3 to 1, then N2 will become 1, N1 will be 3, take the square root, multiply by 3, so I go down to 1.73. So if you centralize all the way down to 1 warehouse, you go from 3 million in inventory to 1.73 million in inventory. To meet the same level of demand, to meet the same service level, everything else stays the same. Okay? So you can see that centralization can dramatically reduce inventories and inventory holding cost. What's the bad side? What's the downside? This seems just really good, right, Tyler?
Because if you're going down to only 1 warehouse, then like your lead times would increase for like all your deliveries to your business.
Right. So distance to customer is a very important metric. The more warehouses you have, the smaller you can make the distance to the customer, right? So you can deliver to the customer much faster. The more you centralize, on average, you're going to be further away from your customer because you can only be in one place. You can be near one customer, really far from the other, or you can split the distance, be in the middle of the 2, right? Or multiple customers like that. So your distance to customer will go up the more you centralize, which means your transportation cost will go up and your lead time to meet customer demand will go up. So there is a price to pay for centralization. It's not cost-free, right? We get into a lot of detail of this in the logistics course. If you take logistics course, a lot of the courses about this trade-off between inventory and transportation cost, well, we play this out in a lot more detail, but not everybody will take it, so at least you should know that there is a downside to it. Now, I want to quickly recap this example. I'm not going to go over precise details. You can do it yourself, but here all we are doing is we're seeing which products benefit more from centralization versus others. So take an example of 2 products, okay? There's product A and product B, okay? And both of these products we sell in 2 markets, Massachusetts and New Jersey, okay? So you can see the demand is given. Massachusetts, what's the demand over 8 months or weeks? New Jersey, what's the demand? And then product B is, you can see it sells much less frequently. It's low demand product, okay? Let's calculate some demand statistics. So for product A in this market, this is the average demand, this is the standard deviation. How would I get this from Excel if I had that table in the last slide in Excel? How would you get the average? What do you do?
You add them up and divide by how many.
Right, or just use the Excel function equals average, or add them up and divide by 8, right, which are 8 time periods. What function would you use for standard deviation? Anybody remember? Equals stdev.s, and just select that data point, you get standard deviation. Okay. Coefficient of variation is just standard deviation over the mean, so it's just this divided by that. So 13 over 39 is 0.34. What does 0.34 tell me? It tells me that my standard deviation is 34% of the mean. So most of the time my variation is between plus minus 34%. Okay. So my variation is about 34% of the average value for this product. The same product in the second market, New Jersey, has a very similar coefficient of variation, similar statistics in both markets. Look at product B, it's much less average demand, much less variation, but look at the coefficient of variation, it's much higher, right? So if you look at the standard deviation, that will tell you there's very little standard deviation in product B, right? Just 1.2 compared to 13. but CV is a lot higher. Okay, so which product is more variable, has more variability, A or B? Why do you say B? It has just one standard deviation.
Because it's, well, whatever your normal order was, it would be like 100%. So then your normal
Right.
what's that?
Exactly. So if you sell something a lot and it varies by a few percent, there's going to be a huge standard deviation even though it's only a few percent. Right? So the percent standard deviation or the percent variability is more meaningful than the raw number. So that's why we look at this more. Okay? And then the total is just a sum the demand of A in both regions. If I was to centralize A into one warehouse, this warehouse would see the total demand like this, with this standard deviation, with this CV. And if I centralize B into one warehouse, that one warehouse will see total demand. You can see it's just the sum of this. This plus this gives you that. Right? And the standard deviation is this, and this is the CV. Okay? So we can then calculate safety stock and average inventory level for each product for each region. So for product A in Massachusetts, you need this much safety stock. Product A in New Jersey, you need this much. Product B, you need this much. And then the total, you need this much. Okay? So you can see in centralization, if you have just one warehouse, the total inventory it will have for product A will be 131, which is less than the inventory in a two warehouse system. In a two warehouse system, you'll have 88 and 90, which adds up to about 180, close to 180. So you go from 180 units of inventory of product A to 130 units if you centralize. Again, the risk pooling effect. Okay? This is exact, because I used the exact demand data and I summed up the demand. This is not like the square root law, which is approximate. This is the exact level that you'll have. The square root rule just approximates it. Here I have the exact demand data, so I can be exactly precise. Okay? Same for product B. So if you compare, in the decentralized system, the total inventory, you add all these four numbers up, okay? The total inventory is 209 units. In the centralized warehouse, it went down to 151 unit. So the inventory reduction was 27% overall for both products. If I look at the SKU level though, product A, inventories went down by 26%, whereas product B, they went down more by 34%. Okay? So what basically I'm trying to point out is that when you do centralize, overall you'll gain inventory reduction, but it will not be the same reduction for each SKU. Highly variable SKUs with high CVs, percentage variation, will get bigger savings than SKUs which don't have high variability. Okay? So the savings would vary by SKU, and you'll get an overall savings in inventory reduction. Does that kind of make sense, or did I lose everybody? Neodo, you have a question? No. Your hand's up.
No.
Okay, so let me just do a quick self-check. What does inventory levels depend on? So let's say I have two SKUs, everything is the same, one has more variable demand, one has less variable demand. Which one will have more inventory? Highly variable one. So variability increases inventory levels. Okay. What about the raw demand level? One SKU has a lot of demand, average demand is higher. One SKU has lower demand, average demand is lower. Everything else is the same. Higher demand because you'll have higher cycle stock, the D/2 part of average inventory level formula. Safety stock will be the same. Safety stock only depends on variability, doesn't care about the average demand level. But the cycle stock, which is when you order a quantity and you get that quantity for average demand, that cycle stock part depends on the demand level. So cycle stock will be higher for higher demand, safety stock will be the same. Okay. What about service level? I have a 95% service level, I have 90% service level. Higher service level, higher inventory levels. Right? What about lead times? I have two SKUs, same service level, same demand variability. One comes from a nearby supplier, one comes from a faraway supplier. Faraway will have high inventory levels because the lead time goes into the inventory level formula, high lead time, right? Great. So you should remember all of these things, or just remember the average inventory level formulas. You can figure these out. So key takeaways are that the higher the coefficient of variation, the greater the benefit from risk pooling, right? The benefits of risk pooling depend on the behavior of demand in the two markets. So if demands are correlated positively, you have less benefits. If they are not correlated or correlated negatively, you have higher benefits. So positive correlation in demand reduces the benefits of risk pooling. Okay. Okay. The last point I wanted to make is when you do centralized, there is an option called tailored centralization. What this means is that you centralize some of your SKUs, but you don't centralize others. So let's say you have 5 warehouses. One is in Ohio, or a central location, which is centrally located in the US. You put all you centralize some SKUs there, but the other SKUs, you keep them in all of the warehouses. Okay. And usually what people do is they look at their slow-moving SKUs, and those are the ones they want to centralize. Why? Because if you look at this example here, look at the SKU B demand and SKU A demand. Which one is slow-moving? B. And where was the benefit more for risk pooling? B. Why? Because slow-moving SKUs have a high coefficient of variation. Their average demand is low, so standard deviation as a percentage of demand, the CV becomes high. Okay? So because they have higher coefficient of variation, they tend to benefit more from risk pooling. So the tailored centralization strategy says that you want to centralize slow-moving SKUs, because you save a lot on inventory costs here. For the fast-moving SKUs, the saving is smaller. You might not pay for the saving in the increased transportation expense. Plus, a lot of customers buy them. You don't want to disappoint those customers by having long transportation times. So these you keep in multiple warehouses. Slow-moving you centralize. And you can see companies do that. If you go to Amazon, the slow-moving SKUs are not available on Prime. You can't get two-day delivery on them, right? Because they're not in the warehouse close in your state. They're in some central national warehouse. So they can't do Prime with them. So Amazon does the same strategy. Great, we are going along really fine. This is kind of FYI. I'm not going to give you something so complicated, but what you can have is that once you have 3 retailers centralized, managed by one warehouse, you can still do echelon inventory management in this case as well. You get reduced inventories here because of risk pooling, and then if you use the echelon inventory management system we talked about earlier, you have even lower inventories in the systems. You can really optimize your inventory like that. So again, if you do echelon inventory management, it's exactly the same system as before, except that you have to sum the demand for the warehouse, whereas this retailer will use D2 to calculate this inventory level, but this guy will use DT, not D2, because it has to meet demand for 3 retailers, not just one retailer, right? That's the only difference, but you can just quickly extend that to this situation as well, which is a very realistic scenario. Companies handle this all the time. Okay, let's go to our last topic, which is service level optimization. By the way, in terms of computation, you should know how to do this. Pretty straightforward. Okay, so a question like this you should be able to answer, and you should know how to do this, which is this example that we did right here, this example here. So calculate echelon lead time by adding them up, calculate safety stock reorder point just like this. So this example you should know how to do. Okay. Also, if I do give you like a product with demand over multiple regions, you should know how to compute these tables. It's really straightforward, right? You just take average, standard deviation in Excel. So if you have some data in Excel like that, you should actually try this. Go home, copy paste this table into Excel, and see if you can come up with these statistics from that table or not, using average and standard deviation functions. So if that is too difficult, let me know, see me, I'll show you how to do it. But I expect you to be able to look at data like this and calculate averages and standard deviations and make a table like this. Okay? If any of this is difficult, I will work with you, don't worry. Okay, service level is the probability that inventory will satisfy your demand. There are 2 measures of the service level which we are familiar with. Cycle service level, which is that percentage you convert into a z-score. This is what becomes the z-score in all your formulas. Okay? This is the probability that during a replenishment cycle, you'll not have a stock out. The second one, which we talked about the week before last, which is fill rate, okay, which by the way is given in your inventory workhorse sheet. It computes the fill rate, is the percentage of demand satisfied from inventory right away without having any stockouts. Okay. Usually when management says we want a service level of 95%, often in their head they're thinking of the fill rate. Okay. and not the service level. So you have to be kind of careful which one it is, because a 95% fill rate might only mean an 85% service level here. Okay? Because usually the fill rate is more than the cycle service level. Okay. However, if you have extremely spiky demand, it can happen that your fill rate actually falls below service level. So you have a service level of 90% and your fill rate is below 90%. Why? Because if you do get a stock out, because the demand spikes, you're going to get a stock out when the demand spikes. The spikes take the demand so high that your stock out is not for 1 or 2 units, it's for hundreds of units. Because the demand just spikes from 10 to like 1200 or something, or 100, right? So when you do have a stock out, it's a very deep stock out, you miss a lot of customers. So you can calculate for a given service level and a given demand variability what your fill rate will be. But basically you need to figure out which metric management is thinking of when they set a policy. Okay, most companies will, let's say, set a policy that we want a service level of 95%, 90%, some level. Okay, so let's do the example 95%. If your policy is you want a service level of 95%, then the straightforward thing to do is you go to every SKU and you set the service level to 95%, and then you calculate what inventory you need. Right? That's a straightforward way. If you do this straightforward way, if you treat all SKUs equally, you will be leaving a lot of money on the table. You'll not be maximizing your profit. Why?
Because the items that have low variability, you don't need the same safety stock.
So you will get a different safety because the service will give you the Z value, but the Z value is multiplied by standard deviation of demand. So the lower variance items will get lower safety stock. Higher variability items will get higher safety stock, but they'll all have a 95% service level. Okay? Any other ideas? Think about it this way. Okay? You are a retailer which sells a phone and sells this bottle. Okay? You earn a lot of money on this sales. You earn very little money on this sale. You don't want them both to have 95% availability. I want this to be 99%, this could be 80%. Right? Because in terms of the money I make, losing one lost sale here is a big deal. Losing 5 lost sales here may not be a big deal. Because the gross margins are different. Right? So the service level optimization says, pick SKUs which are highly profitable, give them more than the policy. The policy is 95, give them like 98, 99. And pick SKUs which are not profitable, give them lower than the policy. And then on average, you will still hit the policy of 95%, but you will be not stocking out on the profitable items, you'll only stock out on the less profitable items. And so your profit will be higher while still meeting the same 95%. Okay, does that make sense? So let me show you a picture we can capture this. So in general, for everything else being equal, you want to set high profit margin, high volume, low variability items to have high service levels, and the reverse of this to be low. So let me show you a picture. So here, the size of the circle shows you the gross margin, how profitable something is. If you are this way, you are less variable. Okay? So low variability SKUs are here, high variability SKUs are here, because this is the coefficient of variation on the x-axis. Low demand is here, high demand is here. So the best thing for us is to have low variability and high demand and big circles. So big circles in this part get more than 99% or 99% fill rate. Okay? Even here, if you have big circles, that's okay. Even if you have low demand on average, if they're very profitable, you want to give them a high fill rate. Then the middle, which is either they have high variability or not a very high gross profit or not a high sale level, we give them a medium level of fill rate. And then the ones which are kind of slow moving and high variability, we give them a much lower fill rate. Okay? And the average fill rate for all these SKUs is still 95. But by dividing the fill rate to different SKUs, we maximize our profits. So there's actually software that you can get where you give the software average demand level, demand variabilities, the gross margin on different items, the cost of a stock out, and it will tell you for each SKU what fill rate to have an overall fill rate of 95% or whatever you specify, but this distribution of fill rates across the SKUs will maximize your profit. Okay? If you don't want to buy the software, you don't have it, you don't have to, you just go look at these variables, and you group the SKUs. SKUs which are high on profit, high volume, low variability, short lead time, you want to give them a high fill rate. So you can make 2 or 3 groups like A, B, C classification or something on these variables, and then give the A class the highest service level, give a middle service level to B, a lower to C. So you'll get close to the optimal profit level by just doing it manually. You can just do it like that. Questions about this? So let me ask a question. Okay. Okay. Let's say you have done ABC classification based on sales, right? Because that's what everybody sees in operations management. You look at sales, 20% of the SKUs give you 80% of your sales. That's your class A items. Then you have class B, then you have class B, C. So you have that classification in your system already. Okay? And you assign class A the highest service level because they sell the most. You assign class B the second highest service level, and then class C the lowest service level, which is what your case for this week also does the same thing. Okay? Have you done service level optimization, or is there something left to do? Anybody? Shane is doing excellent in class participation. I'll give other people a chance. Anybody else? Is ABC on sales enough for our service level optimization? Are we done? Something more we can do? Shane. Right. Think about dollar store. Even if they sell 1,000 units of something, they maybe make 10, 20 bucks on it because they make a few cents per sale, right? So just because you have high sales doesn't mean it's highly profitable. Plus, something could be more profitable but has so much variability that you need a huge ton of safety stock. Because when you increase the service level from like 90 to 92 to 94, your safety stock doesn't increase linearly. It goes up by more than linearly. So going from 90 to 91 is way cheaper than going from 96 to 97. Okay? It doesn't increase linearly. So something could have a little bit higher profit margin but have huge variability, so just basing it on sales or profit margin alone even is not sufficient. You have to factor all these variables in it. Because when you factor all these variables in, then it tells you which SKU gives you the most profit for an additional dollar of inventory you invest in it. Because that's the question we're asking. I have some dollars to invest in inventory. It's like stocks, like you invest in stocks, right? So you pick a stock, it's going to give you high returns. Same thing with inventory. Your dollars that you have, your working capital that you have, which inventory items to invest in to get the most profit, right? And so for that, you want to look at all of these variables because they will tell you where you get the most bang for your buck, and that's service level optimization. Okay. Okay. Any other questions about today? Anything I can go over again? Do people understand this picture? Okay, good. This is very important. Do people know how to do the square root thing, which is right here? Okay. If you don't know, just follow the examples in the slide, follow the lecture. If it doesn't make sense, we can Skype, we can meet in my office, I can go over individually with you. Okay guys, so that's it for today. Feel free to ask any questions you have. Now next, this coming Thursday, we have a case based mostly on inventory management. Okay, so there's question about centralization, which we talked about today. There's question about service level optimization in it. There's questions about inventory levels, whether they're appropriate or not, right? If you don't want to do a lot of math in Excel, you can skip that case. None of the remaining cases has that much calculation as this case does, okay? But I do recommend you do it because inventory management is a very important area of supply chain management. It's good to learn this stuff rather than not learn it, okay?